Okay, so let us have first a quick recap what we did in the last class. So in the last class, we applied free electron model or Sommerfeld model to derive the conductivity of metals, right? And we came up with this expression where two important factors were the mean scattering time and the density of states, right? And we saw a couple of examples how the very minute changes or the minute details of density of states, as well as how the bands are overlapping, they can affect the electrical conductivity of metals, right? For example, in copper, although we have only one valence electron in comparison to magnesium, which has two valence electron, but copper has higher conductivity. Yes, and that is because of the density of the position of Fermi energy with respect to density of the states. Then we discussed one example of like how Fermi energy is very important. Like it is a very fundamental material property. So contact potential is one of such examples where through which actually we can see how Fermi energy is actually equivalent to electrochemical potential of a material. Electrochemical potential means how much electrical work or the non-mechanical work you can extract out of a particular material. For example, in batteries, when you use lithium, let us say, so it depends, the efficiency of lithium ion batteries depends on the electrochemical potential of lithium. Similarly, there are many other applications where you want to do non-mechanical work. There the Fermi energy becomes very important concept. Then we looked at Seebeck effect, where basically Seebeck effect is when you have a material and you maintain the two ends of a material at different temperatures, they can have you will have flow of effective flux of electron from hotter side to the colder side, or because of that basically you will develop a potential field. So this effect can be used for generating energy. For example, like if there is a if there is a industrial plant and there is a lot of heat coming out of that plant, you can utilize that waste heat, the energy which is getting wasted in the form of heat, that can be used to generate electrical energy. Like for example, you can keep this end of the material closer to the source of that waste heat, and this end you can maintain at cooler temperature, or at lower temperatures using some reservoir or some kind of cooling mechanism, and through that you can actually generate electricity. This is actually this effect is also known as thermoelectric effect, and there is a lot of research going on in the field of thermoelectric materials, so that so that we can utilize the waste heat. If you don't know, actually 50% of the energy which is used globally, that is wasted in the form of heat energy. So if we can increase the efficiency of these thermoelectric materials using this, basically which are working on the principle of Seebeck effect, we can utilize a lot of waste heat which is not being utilized as of now, and that is also contributing into the global warming. So in this field there is a lot of active research going on. Actually, it happens to be one of the research area of mine also. We work in my group also, we work on thermoelectric materials. Then we saw, like how based on the the mean free path, the sign of S can be negative or positive, right? I will not go into details of that, otherwise we will not be able to start with the topic today. And then, like this Seebeck effect is also used in many thermocouples, basically to measure the temperature. So if you have two different materials and you can maintain them at two different different temperatures, like their ends at hot and cold temperatures, because of the difference in their Seebeck coefficient, you can utilize that to measure the temperature. Like basically VAB will be equal to A delta T plus V delta T square. So if we measure the potential difference, we will be able to know the temperature difference also. So this effect can also be used as thermocouples, and actually it is being already used very widely. So today we will start. Uh, Today we will start with thermionic emission. Thermionic emission or vacuum tube devices. This thermionic emission actually is used and vacuum tube devices. They are used in a lot of applications, especially ultra high frequency applications like tetrode vacuum tubes that can handle up to 30 kilowatt and provide gains up to 17 decibel. Similarly, in clistrons are also used as amplifier, and they are also ultra high frequency. They are also used in ultra high frequency television transmitters. So these are the devices which are based on vacuum tube devices, and they work on the principle of thermionic emission. So we will look into this concept of thermionic emission. You can see here. So what happens in thermionic emission is, let us look at this picture in the middle first. We have a material which is a cathode, and then we are heating up this material. Let us say we are heating up this material. This is a filament. This is a heating filament, basically, which will be heating this material. What will happen when we heat this material is the electrons which are there in the material, they will gain the energy, right? And some of the electrons which will gain enough energy, like we know that if we want to free an electron from the material, uh, sorry, this should not be here. Phi is the work function, right? So if we provide enough energy to the electrons, which is greater than or equal to the work function of the material, this electron can leave the material, right? Basically, it will become free, isn't it? So as the temperature increases, some of the electrons will gain energy, and they can gain enough energy so that they can exceed the work function of the material, and then they will go and they will basically leave the material and they will become free. Basically, their energy will be zero outside the material. And from we can understand this from this Fermi Dirac function also. This is the Fermi Dirac function. As we increase the temperature, we know that this Fermi Dirac function that will shift towards the higher temperatures. So this here, the temperatures which are shown, T1 is less than T2 and T2 is less than T3, right? So as we increase the temperature, the electron distribution that shifts towards the higher energies. And as I said, if the energy is, if the electrons gain energy which is greater than EF plus phi, here we are mentioning EF plus phi because we are assuming that if we want to make the electron which is here at the bottom, if we want to make that free from the, we are measuring this energy levels from the bottom of this of the band, right? So that's why this energy level is EF plus phi. But if we want to make free, let us say a Fermi electron, then we will have to give only phi, the work function of the, I mean the energy which is equivalent to the work function of the material. If the electron is here, then we will have to provide some additional energy which will be corresponding to this gap also, right? So accordingly, we will need energies for freeing up the electrons. From this Fermi Dirac function, what we can see is, as we increase the temperature, the electron distribution shifts towards higher energies. And as you can see here, the fraction of electrons which are above the Fermi, above the work function of the, above this energy level which is EF plus phi, that also increases. Although here, the difference is very small, but the number of electrons nonetheless will which have energy greater than EF plus phi, those the number of those electrons will increase, right, as we increase the temperature, which means there will be more and more electrons which will leave the surface of the cathode material here and go into this vacuum which is created. We'll see why the vacuum is required, but right now you don't need to worry about the vacuum. Just imagine that we are heating up the material. As a result of that, as we keep on increasing the temperature, as the more and more electrons they will leave the surface of the material. All right, and what will happen because of that? If there is nothing which which is driving the electrons which are exited, which have left the material. If there is nothing else, they will sit at the surface of the material, right? They will be here forming, they will form a density of electrons at the surface of the material, isn't it? Because once they have left the material, there is no other force which will drive them towards any particular direction. So they will remain at the surface of the material, and they will also remain at the surface because there will be certain attractions from the uh, from the nucleus, which is positively charged, right? So they will remain at the surface of the material. And if we keep on, if we continue this process for long enough time, there will be a concentration of electrons which will be developed at the surface. As a result of that, freeing up of electrons from this material will become more and more difficult, right? Because they will be applying a repulsive force on the electrons, so they will basically provide a sort of resistance for the electrons to not come out of the material, isn't it? So there will be a certain concentration of electrons which will be developed here, after which further freeing up of electrons from the material, that will not happen, right? Because there will be enough force so that these electrons cannot move out of the material, right? That is what is mentioned here in third point. Buildup of these emitted electrons at the surface, it will limit the further emission. It will limit the further emission of electrons from the material. So if we want to continue this process, let us say if we want these emitted electrons for some certain applications, then what we need to, and we actually what is desired is that we want the emission of electrons continues. Then what we need to do is we basically need to remove these electrons from here. Somehow we need to provide some mechanism so that these electrons are moved away from the surface. Only then further emission of electrons can continue, right? So for that, what we do is we basically make a closed circuit in which we provide a voltage, basically a positive voltage at the anode, so that these electrons which are emitted from the surface of the cathode, they are driven away from the surface and they go towards the anode material. So basically these electrons which are getting emitted, they will be, now they will start moving towards the anode because of the application of this potential field, right? And also, because there are electrons which are moving out of this material, there will be depletion of electrons, right? In the cathode there will be a depletion of the electrons. This depletion of electrons will reduce the concentration of electrons, right? So this process cannot continue unless we replenish these electrons. The electrons which are emitted from the cathode, they should also be replenished from in the material. So for that, actually this closed circuit, again basically it works for that also, right? Because the electrons, if we are forming this closed circuit, there will be a flow of current or in this direction, and the electrons will be flowing actually in this direction. So the electrons which are going away from here and reaching anode, they will again come back and join, basically replenish the electrons into the cathode material. So this application of voltage basically works in two ways. First of all, it removes the electrons which are being emitted from the surface towards the anode, and then same electrons are being replenished in the cathode material, right? So that is how we can continue this process of emission of electrons. And this whole setup which you are seeing here, this whole setup which you are seeing here, that is kept in a vacuum. The application of vacuum, actually, if you don't have vacuum, if you have gas molecules, then these electrons will can get scattered by these gas molecules, so they will not be reaching towards the anode. We cannot control their movement towards the anode material. So that is why these tubes, this whole setup is kept in a vacuum. Vacuum tube arrangement in a closed circuit is used to move the electrons, and vacuum inside the tube is used so that electrons don't collide with air molecules, and their motion is controlled towards the anode material. All right. Now let us look at this picture here, the last graph. If you look at here, if we keep on, this is the voltage on the x-axis. We have the voltage of the battery, which we are applying through the battery, and this is the current. So as you can imagine, right, as we keep on increasing the voltage, the current, or basically the number of electrons which will be emitted from this material, that will also keep on increasing, right? Because all the as we keep on increasing the voltage, more and more number of electrons which are being emitted from the surface, they will be replenished here basically, right? As we keep on increasing the voltage, then ultimately at a certain after a certain voltage, the current reaches a saturation value. Can somebody tell me why this, why, I mean, what will be the condition for this saturation? How will we reach the saturation current? What will be happening in case of when we have reached the saturation? Anybody can unmute themselves and tell me. All electrons which are emitted by surface reaches. Perfectly correct. Yes, somebody has answered. Who is that? Saksham. Yes, that is correct. So all the electrons which are emitted by surface reach the anode, right? So in case of saturation, all the electrons, because see, if you remember this emission, how many electrons will be emitted from the material, that will depend only on the temperature. That temperature actually which we are providing this by this heating filament, we are heating up the material, right? So how much electrons can emit this surface, that will depend only on the temperature. From here we can see that saturation current will come only when all the electrons which are being emitted, they are moved from the surface to the anode. Basically they are all flowing in this closed circuit, then only the saturation current will reach, right? Because by increasing the voltage, actually we cannot increase the number of electrons which are being emitted. What we can do is that we can basically increase the number of electrons which are reaching from the surface of cathode to the anode. And when the voltage is enough, so that all the electrons which are at the surface, they are moved to the anode, then basically we will reach a saturation value, and that's what this saturation current corresponds to. Okay, so this whole phenomenon is actually known as thermionic emission. All right, and this was a very important experiment in the development of quantum mechanics also. I cannot go into details how the it became a very important, but if you are interested, then you can read more about this thermionic emission experiment. There are a lot of things related to quantum mechanics which started actually from thermionic emission. Then this, if we want to define this current density, that can be defined by Richard Dishman equation, and it comes out that it depends on the work function of the material, which is very obvious, right? Which is very intuitive, that it will depend on the work function of the material as well as temperature. So if the work function of the material is high, the current density will be lower, because you can also see that if the work function is high, there will be less number of electrons which will be emitted. And temperature is, it is directly proportional, like it will increase with temperature, because the higher the temperature, there will be more number of electrons which will be emitted from the material. So that's why it is actually here also there is a temperature factor, so that also contributes only in increasing the current density, right? So it increases, current density increases with temperature and decreases with work function. In this equation actually, which is mentioned here, this b naught, which is Richard Dishman constant, it assumes actually the original equation which was given, it assumed that all the electrons which are reaching the surface, they are being emitted from the surface. All right. But in reality, what also happens is that the electrons which reach at the surface, some of those electrons are reflected back also. There is a reflection because of the surface effect also. So if we take that into account, then we will have a different emission, this Richard Dishman constant, which is effective emission constant. Okay, so the value of this will be given to you if there is any problem. The value of this Dishman effective Dishman constant will be given to you. How it is derived, actually, I did not go into the detail because it is not really required. But you can imagine that the number of electrons that will be defined, we can again use the density of states as well as probability distribution function. From there we can calculate how many electrons will be there which will have energy greater than EF plus 5, right? And when we know the number of electrons which are having energy greater than 5, then the current density is simply and E times the velocity of electrons. So from there we can derive this expression for current density. The derivation is not really in the, we are not going into the details of the derivation. This equation is known as Richard Bushman equation. Any questions on thermionic emission? Any questions? Okay. If there are no questions, let us move to Schottky effect. Before we move to Schottky effect, or let us move to Schottky effect, we'll discuss it there only. So in the previous case, when we were discussing thermionic emission, we did not, when you apply the electric field, there will be force on the electrons, which are actually the electric field will be there within the material also, right? And this electric field also plays a role actually, which we neglected in case of thermionic emission. Like we did not consider how the electric field will affect this thermionic emission. So that we will try to do here in Schottky effect. Schottky effect is actually comes out from the effect of this electric field which is being applied on it. So let us say if we have an electron which is at the surface, which is at a distance x from the surface, the potential energy of the electron can be defined by this theorem of image charges. This theorem actually what the statement of the theorem is: the force on an electron which is a distance x from the surface, it is equivalent to having a charge within the material, basically the same charge but with opposite sign in the material at a distance of 2x. This is actually theorem of image charges. You can read it from there, you can read anywhere actually, you can find it. So from there, the potential energy of the surface, potential energy of the electron which is at a distance x from the surface, that can be defined by this theorem of image charges, and we can plot that like this actually here. All right. Zero is within, if we remember in free electron theory, we have already assumed that the potential energy of electron within the material is zero. So this potential energy of electron we are taking as zero within the material. From there, taking that as a reference, this energy of electron will look like this actually. All right. And because of the applied electric field, there will be another potential energy of the electron, which will be actually E times Ex times E, right? Which is again, x is the distance of the surface. So again, from here also we can, and this potential energy actually will be negative, right? Potential energy will be negative. So this will be a linear curve. Now the effective potential energy will be sum of these two, right? It will be sum of this image potential energy as well as applied potential energy. So that's what we have written. So this effective potential energy, we can say that EF plus phi minus E square upon 6 pi epsilon naught x, which is coming from image potential, and this EXE, which is coming from the applied potential energy, right? So the effective potential energy of the, or you can say the net potential energy of the electron will be this much. And if you plot that potential energy, you can see that it will look somewhat like this, isn't it? This should be understandable, that if we add these two potential energies, the net potential energy will look somewhat like this, right? And because of that, now actually if you see here, if there was only image potential energy, the work function of the material will be phi, right? But in this case now the work function has come down slightly. Basically we have reduced the effective work function is lesser than the work function without the application of electric field, and this is known as actually Schottky effect, the reduction or the lowering of work function because of the application of external electric field. When a positive voltage is applied to the anode with respect to the cathode, the electric field at the cathode helps the thermionic emission process by lowering the potential energy barrier phi by an amount that we will see how it comes. The basically it is lowering the work function by a certain amount, and the current density in field assisted thermodynamic association is current density is given here. Actually, I've not removed it. Sorry, but you can read it here. Basically, the Schottky effect is lowering of effective work function as a result of applying a positive potential or by the application of external electric field, which is actually helping in the thermionic emission of the electrons from the cathode particle. Right? That's what I have tried to explain here. Right? How now actually the effect we can find out if we want to find out this phi effective, what will be the effective work function after the application of this external electric field. That is very easy to find out. What we know this, basically we need to find out where the maxima is occurring and then find out the value of this maxima, isn't it? For that we know the potential energy as a function of x, right? If you take the derivative for finding the position of maxima, we need to do this dp by dx is equal to 0. From there we will get value of x max, and we can simply plug that into this function for potential energy, and then we will get the value of effective, that the value of potential energy that we will get, that will be actually the value of effective work function, and that actually comes out to be this. This is a homework exercise for you. You can verify whether you get the same expression or not. You have to simply take the first derivative of this potential energy, make that equal to 0, and whatever value of x you get, that you have to plug in here and find the value of potential energy, and that will give you the phi effective. The value of potential energy which you will get, that will be the value of phi effective. That you will have to subtract that from EF, then you will get the phi effective. And from here you can see that we have reduced the value of work function by this amount, which actually depends on electric field, the external electric field which we have applied, right? As we keep on increasing this electric field, the effective work function that will decrease, right? This barrier which is required for making an electron free, or basically for the emission of an electron, that will keep reducing. If we keep on increasing the electric field, this barrier will keep on reducing. So we can, and actually, sorry, I have plotted this wrongly. Let me correct that. How it will look like is, if we keep on increasing the electric field, not only it will reduce the phi effective, it will also keep on decreasing. Basically this width of the barrier, that will also decrease. The width of the barrier, that will also decrease as we keep on increasing the electric field, external electric field which we are applying. And once we get phi effective, we have seen this Richard Dushman equation earlier, right? We can simply, you can again have a look at here. This looks like this. So if we replace this phi by phi effective, then we can get the current density here. So that's what we have done here. Everything else remains the same, and we have just replaced work function by effective work function, which we have just derived. Beta is this whole constant which we are getting. We have mentioned that as beta s here. The value you can see here, right? So the current density after from the Schottky effect, that we can get by applying the Richard Dushman equation with effective work function. That's what I was just explaining. As the electric field increases, the potential energy outside the surface bends and the peak becomes narrower. First of all, this phi effective will become lower and lower, as well as the width of the peak. The width of the peak, that will also reduce. And if the electric field is very very large, of the order of 10 to the power 7 in the SI units, then electron can tunnel through the potential barrier. You know what is tunneling? Basically that when in case of tunneling, the electron does not have to overcome this energy barrier. Like normally what will happen is the electron should reach this much energy first, and then it can only go to the outside of the material basically, right? Once it has reached this much energy, then it can be emitted from the material. When the tunneling is happening, what the meaning of tunneling is, actually it does not have to overcome this barrier. It can simply just tunnel through this energy barrier without attaining the extra amount of energy, right? And because there is no role of temperature here, right now, the Fermi energy electron which is there, that can simply emit without gaining any extra energy. So that means there is no role of temperature here, there is only the role of electric field which we are applying. Actually this emission which is happening, that is happening only because of the electric field. That's why this emission is also known as field emission. Field emission is the tunneling of an electron at an energy level F, at the Fermi energy level, through narrow potential energy barrier induced by large applied field, right? This emission is happening only because of the applied field. When we apply large enough electric field, then there will be narrowing of this potential energy barrier as well as shortening of this potential barrier also. Shortening of the potential barrier also actually plays an important role. If you narrow, the peak becomes narrow, but this phi effective is very high, in that case the tunneling is not possible. I will show you what the probability of, there is a how the probability of tunneling depends on these two parameters. One is the phi effective and other one is the width of this potential energy barrier. But you should remember that if this barrier is very high, then also tunneling cannot happen, right? Probability of tunneling depends on the height of the phi effective as well as the width of the potential energy barrier at Fermi energy level. At this level, what is the width of the potential energy barrier? That is another factor, and the first factor is the height of effective work function. We will look at this point later. I'm skipping this point right now. So this is how the probability of tunneling looks like. See, as you can see here, it depends on phi effective as well as the electric field, right? The higher the electric field, the higher will be the probability of tunneling. Also, the higher the phi effective, the effective work function, the higher will be the probability of uh, tunneling of an electron. All right. Yes. This XF, which is mentioned here, right? The width of this potential energy barrier at EF, that you can simply get from the expression here. What you will have to do is that you will have to put the energy of electron to be EF, and from here you can get the value of x, right? There are only two variables. There is only one variable which is x, rest everything will be known. So if you put this equal to EF, the energy of electron, you will get the value of XF, which will be the barrier width, right? Barrier width at the Fermi energy level. All right. So that is why actually we need to apply a very high electric field. Only then the probability becomes significant enough for having field assisted or field emission of electrons. Okay. Again, the current density of the field emission, that can be derived from uh, by using the density of states as well as Fermi Dirac function. Again, we are not going into the derivation of this expression. This field assisted tunneling, there is an equation called Fowler-Nordheim's equation. Nordheim, you must have heard this name earlier also, right? We earlier in the previous chapter we learned about Nordheim's rule for solid solutions. Here again we see the same name. So this is known as Fowler-Nordheim's equation, and from there we get this expression for current density, which is proportional to the electric field. The higher the electric field, the higher will be the current density. It is appearing, the electric field is appearing actually here also. Then C as well as EC, there are two constants which are mentioned here actually. This depends on the work function of the material, and this EC also depends on the work function of the material. Both of these constants depend on the work function of the material. All right. This field emission effect which we have just discussed, that is a very useful concept. Actually, it is used in a lot of things. Actually, one more thing which I skipped earlier. Sharp point cathodes. Why do we need sharp point cathodes? Can you think about why do we need this kind of sharp point cathodes? How it can help? Think about it. You can write your answers in the chat box. How does having a sharp point cathode it will help in having in increasing the field emission of electrons? Yes, somebody is trying to say something. Corona effect. Somebody has written corona effect. Can you explain? Anybody else? Anyone else? Any serious answers? Due to a small radius of curvature, right? What will happen because of the small radius of curvature? The electric field, yes, correct. No, he has given the right correct answer, Gopal Dev, that electric field will be higher, right? Because of as we have as we decrease or as we reduce the radius of curvature, the electric field which will be generated at this point that will be higher, right? We can increase the electric field significantly by making these kind of sharp point cathodes actually, and that helps in increasing the intensity of field emission. That's correct. Right. Okay. So this is how actually a typical setup of a field emission uh, of the field emission looks like. What we have here is this is our substrate on which we are building the device. Then we have this cathode, sharp point cathode here, right? Then we are applying a biased. Basically, this is a gate, and this is positively biased gate actually. What it does is that because of this positive biased gate, we will develop the electric field at this point, isn't it? And then the field emission will start. Here on the anode, on the surface of the anode, we have these phosphor materials. These phosphor materials are actually the materials which can provide you cathodoluminescence effect. So what happens is that these electrons which are coming, which are being emitted from here, they will collide with the electrons in this phosphor material. Phosphor materials are a special class of materials where when the electrons emit, they can produce the photons of different colors, so we can actually generate different type of colors which are used actually in televisions. This technology is a little bit older now we have LCD screens, but like few years back we had these television screens which were built on this field emission effect. So what happens is that these electrons which are being emitted, they will go and collide with some of the electrons in this phosphor material, and because of that there will be emission of different colors, and then they can be used for, and these phosphors actually they are for different kind of for different colors of phosphors we use different type of materials. So depending on what color we need, we will use that particular material, and then we can use this field emission effect for generating vibrant colors on your screen, and that can be used in a television or any kind of display screens, right? Both the gate as well as anode, they are positively charged with respect to the cathode, right? In this case, although if you remember earlier, we did not use this gate concept. Here we are using gate because it is closer to the cathode material, so we can generate the electric field more effectively by using this gate sort of concept, which you must have heard in your semiconductor devices also. this kind of gates are used very often. As we increase the gate voltage, this is the uh, this is the current density which we will get, right? As you can see, once the gate volt initially, it is uh, the anode current is not increasing much more very rapidly, because actually once the gate voltage reaches a threshold value, only then the emission starts. So let I think we can say here that from here there is almost a exponential increase in the anode current which we are getting, because the emission will start only after reaching a threshold value. Again, if we plot, wait, yeah, I think this you can forget about this curve, because we have not discussed the equation for this kind of, what will be the equation for the anode current. But what we can see here is that as we keep on increasing the gate voltage, after a certain voltage the field emission will start, and then it will keep on increasing as we keep on increasing the gate voltage. This cathode, this kind of cathode which we are seeing here, that is known as spin type cathode. It comes from the person who actually discovered this type of, or who invented this kind of cathode. And it is basic structure of one of the pixels in the field emission device. Because why I'm saying one pixel, because this will generate only one type of electron. If you want to make, sorry, one type of color, if you want to make a full screen, then you will have to have very closely spaced spin type cathodes, which, as you can see in this is a microstructure which is taken with scanning electron microscope. And as you can see, there is an array of these cathode tips, right? There is an array of cathode tips, and on the top you will have different phosphors for different colors. All right. And because of that, you will generate different type of colors on the screen. Basically, these are images at higher resolution. So this is only one single tip which you can see here, and this is a closer picture at that particular tip. It looks like a hill, right? So this is, or iceberg, it looks like an iceberg. And this is how the field emitted screens or displays are manufactured. You can see this is an example of field emission display, field balance display, right? Nowadays actually there is a lot of research on carbon nanotubes. These carbon nanotubes are, apparently they are very effective in generating these kind of devices, because the essentially what a carbon nanotube is. Carbon nanotube is single layer of carbon molecules wrapped into a tube, basically, as you can see here. So these are carbon nanotubes. If you cap them up with the fullerene atoms, then actually this can also be used as in the field emission displays. You can see there is an array of these carbon nanotubes here, and this micrograph is showing a single carbon nanotube. Okay. And actually, you might be thinking that because this radius of curvature is not that small, right, in comparison to when we have this sort of tip, right? The electric field should be larger here. But experimentally it has been find out somehow, in case of carbon nanotubes only, in case of this kind of single walled carbon nanotubes, the electric field is higher actually in comparison to this kind of very sharp tip. The reason for that is still not very clear, but it comes out, certain effects of the particular material which we are using, that is carbon nanotube. So the intensity of carbon nanotubes in field emission is higher than in these in comparison to these spin type cathodes. All right. I think, yeah, this is again showing, similar sort of thing which we just discussed. As you can see, there are different color of phosphors which are being used. Basically, cathodoluminescence effect. These materials, they are cathodoluminescent, and they are using different colors of phosphors for generating vivid colors on the screen. All right. So we are done here with our lectures actually for this unit. If you have any question, we can discuss them now. We have still some time, I think 5-10 minutes we have, so we can discuss them now. Any questions? I think next week we don't have. I don't think we will have any lecture because there is midsem break, right? So next week there will be midsem break, and we will meet only week after that. The next assignment, the assignment which has been already uploaded, that is due on 17th, I think. So please submit that assignment on time. And during this week, I mean midterm break, probably I will also post the next assignment because we have already finished this chapter. So there will be one more assignment. Of course, the deadline for that assignment will be, you will have enough time to submit that. All right. Any questions? Any doubts? No.